Hello everybody. This is the video for lesson 1.2, limits. Okay, so what exactly is a limit? In the last lesson, we talked about rates of change, specifically looking at the slope of a secant, which gave us an average rate of change between 2 points, finding the tangent line, which also gives us the instantaneous rate of change by finding the slope of a tangent line at a particular point. Now today what we're going to talk about is limits. And what exactly is a limit? Well, if you're watching this video, I'm assuming that you have attempted the worksheet and you have taken a look at the video that was attached in that worksheet. And the video should look like this. So if the link doesn't work, just type in calculus, the limit of a function, and it should be made by my secret math tutor. And this video explains it pretty well in about 4 minutes what a limit is. Okay. Now we are going to examine it algebraically here. So using this worksheet, we're going to see here that we have an equation y equals 2x squared minus 2. And we want to find out what the limit is as x approaches 3. Okay. So how does that work? Well, let's use the same analogy that was used in the video, that if we're going to start at 2, we're going to say 3 is essentially where the fridge is. Okay? We're going to say that's where the fridge is, based on the analogy used in the video. So what we're going to do is sub in 2 for x and see what we get. Okay, so now I have Desmos open in the background. So 2 for x, and I'll get 2 squared minus 2 is 2. So I get 2. Okay, what if I replace it with 2.5? 4.25. Okay, replace it with 2.9 and I get 6.41. Replace it with 2.99 and I get 6.94. And what about 2.999? 6.994. Okay, and then what happens if it's 3? So we've essentially reached our fridge. We get 7. Okay? So that's approaching it from the left side. So just to kind of add on to the analogy that was used in the video, let's pretend 2 is where the couch was. Okay? Let's pretend this is where the couch was and you're approaching the fridge. Okay? And then let's start at 4. And let's say 4 is where the bedroom is. Okay? And then you have that same craving for pizza. So we're going to start with 4 and we get 14. 3.5, we get 10.25. 3.1, 7.61. 3.01, 7.06. 3.001, 7.006. So you can see approaching it from said, I just made this up. Let's say this was the bedroom. Okay. You're still heading to the same destination. Okay. Which in this case is the fridge. So your limit, we can say, is still 3 from both sides. From looking at this table, you can say the couch is the left side, and you can say the bedroom is the right side. Okay. Now examine the values in the table that are to the left of 3, beginning with x equals 2. What value is y approaching as x gets closer and closer to or approaches 3 from the left? Well, what value is y approaching to? 7. Okay. Beginning of x equals 4, what value is y approaching as x approaches 3 from the right? So that's from the bedroom. We're approaching it from the right. It is also approaching 7. Okay. So now reflect. So we're going to compare the values you determined for y in parts B and C. What do you notice? Well, from x equals to 2 to, I think it was 3, right? Yeah, from x equals 2 to 3. Let me me scroll down a little bit here. From 2 to 3. So x is 2. Whoops. Let's flip this over. From x is equals to 2 to 3. And then, so that's from the couch. And then now from the bedroom, when x is going from 4 to 3, well, what is it approaching? A y value of 7. Okay. Now, as the video has said, well, can't I just plug in 3 to get 7? You can, assuming the point exists. In this case, it's a parabola, it's a quadratic function, it does exist. However, that's not always going to be the case, which you will see later. Now, the value that y approaches as x approaches 3 is the limit of a function. In this case, our function is y equals x squared minus 2 as x approaches 3. How do we write that? Well, we write it as two limits. We write it as a left-hand limit. So again, this is from the couch. Okay. So the left-handed limit as x approaches 3 from the left. So this little minus sign represents from the left. Well, what's the limit in this case of fx? And fx is x squared minus 2. The limit as x approaches 3 from the left of fx is 7. Okay. Now we check the same thing for the other side. So this is, in this case, from the bedroom, or from 4. Okay. So limit, the right-handed limit as x approaches 3 from the right is going to be 7 as well. Now, if both the left-handed limit and the right-handed limit are the same, which they are, then we can say the limit as x approaches 3, notice how there's no left or right side, is just the number 3. Limit of fx as x approaches 3 will equal to 7. Sometimes you might see it written like this. Limit with an x approaches 3 underneath. Instead of fx, you're just going to see the function itself. So we can just say x squared minus 2. Okay. I like to include brackets just to clean it up a little bit. It's going to equal to 7. Okay. So in summary, limit as x approaches a of fx exists if the following criteria are met. If approaching from the left side, if that number exists, which sometimes it can't, it might not. So a scenario might be if you end up dividing by 0, for example. You can't divide by 0, which means the limit doesn't exist. Or the limit x approaches a from, or a number from the right also exists, and those two numbers happen to be the same, then we say the limit of fx as x approaches a exists. Okay? So a scenario where it doesn't exist might be, this is just a very rough example. So let's say, I don't know, I'm just going to draw something like that, and then something like that, and then let's call this, let's use the same numbers. Let's say this is 3, this is 6, this is 7. So in this example, I will say, okay, so the limit as x approaches 3 from the left, so from the left would look something like this. Okay, so I'm going to use green to represent that as x approaches 3 from the left of fx. Well, what does it equal? From the left, it looks like it equals to 6. So I say that equals to 6. Now let's use orange to approach from the right. So what's the limit as x approaches 3 from the right? As x approaches 3 from the right, it equals to 7. Well, look at that. These two numbers are not the same. 6 and 7. Don't say it. They are not the same, so we say the limit as x approaches 3, the limit of fx as x approaches 3, we will say does not exist. Okay, for this particular scenario that I just made up. Okay, so let's take a look at a quick example here. Determine if limit of x approaches 4 exists. If so, state the limit. So our first job is limit as x approaches 4 from the left of fx. Does that exist? So there's 4. Okay, now from the left, so left-hand side of the dot, the limit as x approaches 4 from the left of fx is -2. Now from the right-hand side, limit as x approaches 4 from the right of fx is equal to, from the right, it's still -2 as well. Both numbers are the same. Okay, so limit of x approaches 4 from the left of fx is equal to limit as x approaches 4 from the right. Therefore, limit x approaches 4 of fx, it does exist, and that number is equal to -2. Okay. For fx equals 2, example 2, sorry, determine if limit of x approaches -1 of fx exists. If so, state the limit. So we're going to do the same thing, except we're just doing it algebraically now. So limit as x approaches -1 from the left of fx is equal to, well, instead of me writing out the entire equation, I'm just going to type this in my calculator. So it is 7x4 plus 2x, oops, 3, where those x's are, I'm going to replace those with numbers, so I might as well just leave them blank, minus 12x squared, and minus 4. Okay, so I would write all this out, okay? And then if I'm approaching -1 from the left, okay, and sometimes we struggle with trying to picture what number that is, draw a number line. So 0, -1, 1, -2, 2. Okay, so if you're approaching -1 from the left, that means that's these numbers over here. Okay, so think of a number that's very close to -1. I'm going to choose -1 point. What about -1.001? Okay, that's to the left of -1. So sub that in. Now, of course, I could just graph this on Desmos and look at it, but you won't be able to do that on assessments. So you need to be able to do it, solve it algebraically, which gives you roughly -11.00, I'm going to say 2. So -11.002. Okay, now let's test it from x approaches -1 from the right of fx, and that equals 2. Well, from the right of fx, or a -1, so that's a number very close to -1 from the right hand side, and that would be what, -0.99. So let's do that. -0.99, 0.99, 0.99. That gives us -10.98. 10.98. Okay, so in fact, if I wanted to be more accurate, I want to get even closer. Let's add an extra 9 on all these. -0.999. -0.99999. Negative. And look at that number now. -10.99, which is actually pretty close to negative. -10.997. -10.99. Let's round that to 8. Looking at these two numbers, they look like they both approach roughly -11. So we can then say the limit as x approaches -1 of fx, since they're both the same, is -11. And yes, it does exist. Okay. Last example. Sketch the following function. Okay, so I'll start there. So x is saying ct is equal to 3. Okay, so this is called a piecewise function because there's 3 different pieces to it. Okay, so I have ct equals to 3, which means I look at 3. Okay, now it only equals to 3 when t is between 0 and 20. So 10, so 20 is right there. Okay, and does it equal to? Yeah. So it can be less than or equal to. So since it could be less than or equal to, so there's 20, right? I would draw a closed dot to represent that it's equal to as well. So which means between 0, so starting at 0 to 20. Okay, from 0 to 20, ct is equal to 3. Okay, next one, ct is equal to 5. When t is bigger than 20, less than or equal to 40. So 20, 30, 40. So there's 40. So I know that at 40, so first off, it is equal to 5. So there's 5. So that means I know that at 40, it's going to close dot. And at 20, let me just double check. It is strictly less than, not equal to. So which means at 20, this would be an open dot. Okay. And last but not least, ct equals to 7. So 7, when t is bigger than or equal to, sorry, bigger than 40, not equal to, strictly bigger than 40, but less than or equal to 60. Connect those two, and there's our last piece. Okay. Now, oh, I made a mistake at the very beginning, didn't I? So this line here, I should have an open dot at 0 for the same reason I have an open dot at 20 and 40. Okay, because at 0 it says strictly bigger than 0, not equal to. Now this is still a function because it passes the vertical line test, meaning if I were to draw a vertical line anywhere, I would only ever cross it once. So if I drew a vertical line here, or here, or here, okay, it passes the vertical line test. Okay, and now if I were to draw a vertical line here as well, does this pass the vertical line test? It does, because this dot is closed, but this dot is open. So technically it does not cross my function in more than one spot. Okay, so let's get rid of that. That was just a little revisit to what a function is. Okay, now, so we want to know if this exists. Well, let's find out. So the limit as x approaches 20 from the left, so 20 from the left, so that's over here, 20 from the left, what is that limit? It looks like it's approaching 3. Let's use purple. Okay, what about limit as x approaches 20 from the right? 20 from the right. Okay, approaches 20 from the right. It looks like it's approaching 5. Huh. Is 3 the same thing as 5? It is not. So we then say the limit as x approaches 20 of the limit of ct as x approaches 20 does not exist. Okay, awesome. As always, if you have any questions, feel free to shoot me an email. We'll talk soon. Bye-bye now.